Hello everyone. In this short video I want to show you how to approximate a function in TensorFlow. So remember, one of my previous videos was using add-a-line networks for function approximation. So here I'm going to use something similar, but I'm going to use ReLU function instead of sigmoid. I also show you what happens if you use a sigmoid function. And the function I want to approximate is the sine function here, sine 0.3 times sine of 2x. Between range -2 to 2, I use 100 data points to train this network. So you see I use a sequential model. The first layer is a dense layer with 20 neurons, and the input shape is just 1, which means a scalar. The activation function is ReLU, and the last layer is of course a simple dense layer but with only 1 neuron. Okay, because the output is a scalar as well. So input is a scalar x and output is a scalar y. If it was a multivariable function, so like it was z as a function of x and y, this guy would stay at 1, but that one will be like a 2. Okay, because you have 2 inputs. And here I use Adam as my optimizer, but I use a higher learning rate than the default, because if I don't, then it is going to go very slow, and my cost function, which is MSE in this case, is not going to go down significantly. So I bump up the learning rate significantly here, so it allows the regression to do a good job. And of course, for my last layer, I'm not going to use any activation function because it's a regression. And I'm going to use my entire x and y data here to train my network. And I use a lot of epochs here to make sure the error goes down as much as possible. So I use 500 epochs. You can do more. This is rather fast because it's a very simple model with simple x and y. And so I allowed it here to go down by 500, right? So let me run the code for you part by part. So this is where I get my x and y. This is where I define my network. This is when I train it. And you can see that it goes pretty fast here on GPU. So 500 epochs is not a big deal. And it should be able to finish it quite a bit fast. And you see now the loss function is of order 10 to the -5, which is really good. And so now if I plot my loss function, you see that from 0.2 or above 0.2, it goes down to very close to 0. And now I can plot my original data, and also I generate a bunch of new data in the same range -2 to 2, but using random generator. So I use the TF random uniform, and I use the same number of points, 100 data points, but this time randomly between -2 to 2, not the same as the original training data. And I convert them to NumPy because you know the data generated by TF random are not NumPy arrays, right? They are eager tensors. So I convert them to NumPy, and then I pass them to model.predict. So it gives me the y values or the predicted values. And then on the top of the original curve made by the training data, I also plot these new test data and the predicted data for them, and using blue circles. And I use a legend, so I show you whether they stay on the top of each other or not. And you can see they do. So this is the curve made by the trained data points, 100 of them, and you see it beautifully shows the 0.3, right? You see the amplitude is 0.3 times sine of 2x. And you see that all of these blue lines fall on the red line, and you see clearly they are not uniformly spaced, right? They are random, and they are doing a great job here. Okay, so it is doing a great job with the ReLU function. And so now you might say, what happens if you change this ReLU to sigmoid, huh? So if I use the same network, but I use a sigmoid function instead of a ReLU, could I get anything close to what I just got? Well, let's go ahead and find out. So here we go and run the whole thing and see if we can get any good results. Okay, so you see the error is 10 to the negative 4, so it's not bad. But let's find out. Okay, it's trained. The error, you see it is going down. And it's not really bad, I would say. It's not too bad. It did a relatively good job. And not as good as Relu. Relu was quite a bit better. You didn't have these deviations, but you see the Adeline network here. This is an Adeline network with 20 neurons. It did a relatively good job. Okay. Now you might say, what if I bump up the frequency? So I make the function oscillate more, so it is harder to train it, right? The faster the function is oscillating, it is harder for the network to train that. So I bump up the frequency to 4 now. Okay, let's see what happens. So I increase the level of difficulty here, basically. And again, let it go down. And you see here, the cost function is not going down big time. Look, still 0.04, so it's not really a good job. And clearly, you should not expect any amazing result here. And there we go, you see. The frequency went up and the network could not keep up with it, okay? Now, you might say, well, change it back to ReLU. You might be able to get it, right? Well, let's find out. If the difficulty of the function is bumped up, whether ReLU can do a miracle. Okay, so you see here, clearly the errors are much smaller than last time. So probably it is going to do a little bit better job, but let's find out. Okay, and you see it's not bad actually. And it's not amazing, but it's not too bad. I mean, there are some big errors here. Not big, I mean relatively, like here you can see it goes from 0.3 to like 0.38 or something. So it is not small, but not crazy big. But it's not bad. So you see clearly ReLU is doing a better job than Sigmoid does. And the other thing is, well, if that's the case, can I bump up my neurons and make the error better? So if instead of these 20 neurons, if I make it 40 neurons, would that do a better job? Well, you have to first of all be careful not to do overfitting. You have 100 data points here, so you don't want 100 neurons, okay? But let's see if you bump up the neurons will make the result quite a bit better. Okay, so the training is being done. Let's go down. And you see, not much better actually. You have the error now on this side. Okay, so you see now I have the neurons on this side. And it did not do a much better job. Okay, although still not bad, but it was not like perfect. So you might say, what if I break down these 4D neurons into 2 separate layers? Okay, so basically come here and add a second layer with another 20 neurons or maybe 10 neurons or something like that. Use another ReLU function. Okay, output is still 1, right? So you see here I have now 3 layers instead of 2. And bring down these neurons between them, so maybe 30 and 10, okay? Still use the same learning rate, no change, the same cost function. What about this one? Okay, so I'm showing you all different ways you can think about bringing down the error, right? So you can play with them when you have the time. So you see the errors are not bad. They are 10 to the negative 4. It's not bad. You go down, you see here, basically you have a lot of oscillations. Okay, so here you're not doing a ton. This part was amazing, but this part is not. And if you look, actually it's better than last time. Those big overshoots you have are reduced. Okay, here in the beginning, of course, you're going to have a little bit error, but in the middle, it's not bad. So maybe one of the things you want to do is, instead of adding all the neurons to one layer, break them between several layers and make it more of a deep learning, really, right? And again, if you want to avoid overfitting, You can add what? You can add some dropout here. And remember, it was what? It was tf dot keras dot layers and dot what? Dropout, huh? With a capital D. You see that here. And with some probability for dropping. So you're not overfitting. And this should definitely not bump up the results for you. Let's see. And there is a comma, I guess I have to add. Right, so I have now 4 layers. Of course, this is not like much of a layer, really. It's just getting rid of overfitting. But let's go ahead and see. Again, it should not really improve the results. It's not, because it is removing some of your neurons, really killing some of them. It's just to not overfit. Okay, so if you have test data or training data or validation data, actually this helps not ruin the training test. Or so you see here clearly you're not going to get that good of a result. I'm just telling you, if you're using a lot of neurons here, you might want to consider adding a dropout. But here, this is not a ton, and so I might just go back with what I had. Okay. The other thing you might think of, can I make this learning rate more aggressive? If I make it 0.05 instead of 0.01, what would happen? So let me show you that one. So here I'm going aggressive, and aggressive is not always good because you can overshoot. You see, look at your loss function. Now it's not doing a good job. It's all 0.01. It's not really going down well. It's too aggressive of a learning rate. Okay, you might use a scheduling function, right, to drop it as it goes down, right, and the epochs are going down, but you clearly see here, look, that is very bad here. The rest of it is not bad, but this part is horrible. So you might not want to go super aggressive, and you might say, what if I bring it down in the beginning and add to the epochs? So instead of 500 epochs, right, when I do this portion, where is it here? So what about I make it like 2000 epochs, right? Would that do a better job? So here, let's find out. Okay, I let it go all the way to 2000 epochs, and you see again here you have all these oscillations. So literally beyond 500 epochs, you are not going down further, okay, and just oscillating. So so it's really the learning rate made this initial part maybe a little bit smoother, but afterwards it's not really doing a ton. You're oscillating. So maybe when you go down here, you might want to change your learning rate. And again, you have to use a scheduling function, which I showed you in one of my previous videos. But you see the result is not actually bad, and I could learn this higher frequency function. But again, it's not much better than the previous one, okay? And so it's not really bad, but there are so many things that you need to select, from the number of layers to the number of neurons in the layers to the activation functions, to the learning rate, whether you want to change learning rate, whether you want to use Adam optimizer or you want to use a stochastic gradient and use some momentum, right? Here, when you see it's plateaued, maybe you want to change that. The MSE is really good for this kind of regression. You don't want to change that. But there are a lot of things, the number of epochs and so on. So you have to play with the network and see how best you can train the function, okay? There are some general guidelines that I told you about, but in general, there is not one magic formula for it. But in general, when you see that the function is going down fast, like this, you might bump up your learning rate, and when it is slowing down, you might want to reduce the amount of learning rate. And if it keeps going up, you might want to undo whatever you did and add more to the momentum. Okay, if you're using SGD, because Adam method does not use SGD, does not use momentum, I'm sorry. So these are just some of the things I told you. Hopefully it was useful to you and you learned some basics about approximating a function in TensorFlow. Thank you so much for your attention. I'll put this file, the download link for it, under video description, and I'll see you next time. Thank you.